This lecture is a supplement for Thursday, September 27th. We spent the lecture reviewing problems for the quiz 2 on Monday, October 1st, but I promised that I would cover some material that would be helpful for the homework assignment due this weekend. And it's actually some important topics. I have to admit, your textbook doesn't really cover this in very much detail, but I think it's actually important to cover this well so that you have a sense of how you apply Newton's laws. So the topic of the supplement is applying Newton's laws. And I know you're rather busy this weekend, so I'm going to go through this material without rewriting the notes and just go through the notes. That way the lecture, the video, will be shorter than an hour, or at least I'll try to make it shorter than an hour. So let's get started. Okay, so we're going to apply Newton's laws. Remember Newton's first law, Newton's second law. We won't really be doing much with Newton's third law at this point. So let's consider two blocks that are attached by strings and are accelerating at 1 meter per second squared on a frictionless horizontal surface. The masses are 1 kilogram and 2 kilograms. I'll call it M1 is 1 kilogram, M2 is 2 kilograms, so you can remember which one is which very easily. It's an example I sort of hinted at before in my lectures, having these two masses being pulled to the right. Okay, so the problem is, find the tensions T1 and T2 in the strings shown. We have a tension T1 here. For this string, remember, the tension pulls both sides of the strings inwards towards each other. So there's a force pulling this way, T1. There's a force pulling this way with a magnitude T1. And then this is tension 2 that's pulling in this direction for on M2. And you're told that both masses accelerate with 1 meter per second squared. Suppose you want to first calculate T2, the tension on string 2. There is a rather easy way to get the tension on T2 if we consider both blocks together as one unit. Okay. That way, T2 is the only force acting on this unit, and we can use the Newton's second law to figure out what T2 must be. Okay, so that's the strategy. We consider the free body diagram for M1 and M2 considered as a unit. The net force is just this T2 going in the positive x direction. We take positive x to the right. Now, what we will do is we will look at the net force. So I said the net force, there's only one force, it's T2, pointing in the positive x direction. So now Newton's second law says that the net force will be equal to the mass times acceleration if we're just going in the x direction, so F net is equal to m times a. But that net force is just T2. That was the only force acting on our system. T2 is the only force. So T2 must be equal to the mass times the acceleration. Okay, but remember, what is this mass? It's M1 and M2 put together. And so the total mass of this guy is M1 plus M2 times the acceleration. Okay. M1 plus M2, that's 1 plus 2, or 3 kilograms, times the acceleration, 1 meters per second squared. That gives 3 newtons. So that's how we get T2. Now, considering both blocks as one unit won't help us get the tension for tension for T1. For that, we should consider one of the blocks separate. Okay, so we could consider M1, or we consider M2. Now, I'm going to be lazy here because M2 is kind of complicated because it has T1 and T2 touching it. I'd rather try to get the answer as quickly as possible, so I prefer looking at M1 because the only force acting on M1 is T1. Force going like this. So to solve for T1, we just consider the mass M1. So we have the free body diagram for M1, and we have T1 pulling on it. And we know it also accelerates with 1 meters per second squared. This is our positive x direction. So now Newton's second law gives that F net is equal to ma. We're looking in the x direction. So T1 is the net force. Ma must be equal to ma. Now in this case, we only have the mass m1, and so we have m1 times a. That's 1 kilogram times 1 meter per second squared, so that's 1 Newton. So that's how we can get the tensions T1 and T2. So in summary, this is what it looks like. If we pull 1 kilogram here, 2 kilograms there, we're pulling with 3 newtons over here with T1, and the string in between, 3 newtons for T2 over here, this was T2, and then 1 newtons for on this string over here, 1 newton this way and 1 newton that way. Okay. Hopefully that makes some sense. This string has to have a larger tension because it's pulling both of the masses. This is a smaller tension by a factor of 3 because it's pulling only 1 kilogram. Okay, now the next topic is inclined planes, and this is probably the one topic your textbook doesn't seem to cover very much at this stage, but I think it's important to explain this in detail. So an inclined plane is basically a plane that's not horizontal. As you can see here, a ramp like this. So let's first consider a frictionless inclined plane at some angle theta. So the angle of incline will be measured from the horizontal. And let's put an object on it, and we'll consider the forces on the object. We start off with something that's frictionless. Okay? Frictionless means you can slide up and down the plane without any force acting on the object. It just slides up and down. If there were friction, then it becomes more complicated. Friction is something we'll discuss on Tuesday's lecture, October 2nd. Okay, here's an important fact. If the inclined plane is theta, this angle theta, then the angle between the normal force, remember the normal force is perpendicular to the surface, so the angle between the normal force that the inclined plane exerts on the object and the vertical line is also the angle of theta. Okay, let me try to show this with diagrams. So if I've inclined the plane by an angle theta here, if I draw the perpendicular to the plane, so notice this line here is absolutely vertical. This line here is not vertical, it's perpendicular to this inclined plane. But notice that the angle between the normal to the plane, to this plane here, this guy is perpendicular to this plane here. It makes an angle of theta with the vertical line. Okay? Hopefully that's clear to you. If I make it a big angle, then the normal vector is tilting even more. It makes an angle of theta with respect to the vertical line. Okay, let me say that again. The angle of incline, theta, is the angle between the normal vector, not the vertical. This is normal, meaning perpendicular to this tilted surface. The theta, this angle, is the angle between vertical and the normal to the tilted surface. Vertical, tilted surface, the normal to the tilted surface. Okay? So, hint, if you draw theta so it looks small, then this is kind of just obvious by looking at the angle. As you can see, there's only a really small wedge here, just like this really small wedge here. Okay, and now the whole strategy of studying inclined planes is that instead of considering horizontal and vertical components, x and y, you consider parallel and perpendicular components, parallel being this direction up and down the plane, perpendicular being normal to the plane, perpendicular to the plane. Okay? The reason why we adopt this strategy is rather simple. And I've actually written this out as a question. We usually consider the x horizontal and y vertical components of forces. We usually consider horizontal and vertical. We call them x and y. So the question is, why for inclined planes do we consider force components that are parallel and perpendicular to this tilted inclined plane surface? And it's actually a very smart reason, a very simple reason. The reason is because the object is only moving parallel to the inclined plane surface. We don't solve problems where the inclined plane is, where the object is jumping off the inclined plane. It stays on the inclined plane. It only slides or goes up and down the inclined plane. It doesn't jump off the inclined plane. Okay? There is no motion in the perpendicular direction. There's only motion in the parallel direction up and down the plane. It only goes parallel to the plane. Since there's only motion parallel to the plane, that means getting components parallel and perpendicular to the plane is really a very simple and helpful way to get to solve problems. So getting the parallel and perpendicular components is the easiest way to solve the problem, and that's basically the reason why we do it. Okay, now one comment I should make, since we're not using vertical and horizontal components, you may be susceptible to doing the vector decomposition incorrectly. So I want you to avoid this. And note that when you get the components of the vector, that vector that you're resolving the components of must be the hypotenuse of the right triangle. It should not be one of the legs of the triangle. So for inclined planes, we will do something that might seem kind of weird. We get the parallel and perpendicular components of the force of gravity. Because gravity goes straight down vertically, it's not in the perpendicular direction or the parallel direction. So we need to get the components of the gravitational force, the force of gravity. Okay? So these are the components. This is going to be the parallel component going down the plane, and this is the perpendicular component going into the into the plane that way. Okay. Now, one thing I should mention: this thing is wrong. It's an exclamation mark. This is not how you resolve gravity. If you draw something like this, it's completely wrong. You've drawn the leg of a triangle, right triangle. When you resolve a force, like gravity, it must be the hypotenuse of the triangle. I've seen students draw this and get all mixed up. You draw gravity, but it's the hypotenuse of the triangle, and you're resolving the perpendicular and the parallel components. Okay? So this is not right. Okay, now let's go on. Let's do an example. A mass of 2.0 kilograms is placed on an inclined plane with an angle 30 degrees, as shown here. 30 degrees. How fast does it accelerate down the plane if there is no friction? The second question is, how big is the normal force of the plane? So the normal force is perpendicular to the plane. How big is that angle? How big is that force? All right, the first thing we do is we draw the free body diagram. The force is on this mass. So we have gravity going straight down. So that's the force of gravity going vertically downwards. So notice Fg is the force of gravity, and it points vertically downwards. Now Fn is not going straight up. That would be wrong. Because the inclined plane is tilted, the normal vector is also tilted by the same amount, 30 degrees. So there would be a 30-degree angle here. All right, so Fn points perpendicular to the inclined plane surface. Let's now resolve the vectors into parallel and perpendicular components. So I like to call it parallel and perpendicular. Your book likes to use x and y, or x prime and y prime. I find that very confusing because x and y for me is horizontal and vertical. So that's why I will stick with the notation that I've used for a number of years. So parallel, okay, the symbol for parallel, I will mention that later, is two parallel lines like this. That's what the symbol for parallel. And the symbol for perpendicular is just these lines that are perpendicular to each other. Okay. So my convention will be the parallel, the positive direction will be going up the plane. Okay? The reason I like that is because we like to think of things pointing upwards as being positive, I know that if you just let it go, the object will fall down, but that's like gravity. Gravity goes, things go in the negative direction. But so we'll take the positive direction to be going up up the inclined plane. We'll take the positive direction to be going off the plane, leaving the plane, out of like that. Okay, the plane's here. You're lifting the object off if you're going in the positive direction, perpendicular direction. Okay, now it's useful to be explicit about which direction is positive for each component. Okay, so now let's consider the normal force and the force of gravity going vertically downwards. Let's first consider the parallel direction. Okay, that's in this direction here, parallel to the surface. Does the normal force have any parallel component? No, it's perpendicular to the surface, so there's no parallel component whatsoever. Okay, so no contribution to the parallel direction. Now the Fg, the force due to gravity, it has a parallel component, and it's going down the plane because I took this to be positive parallel direction. Okay, and this angle is theta, so this is the opposite side to theta, so it's Fg. Fg is this hypotenuse times the sine of theta, and it's pointing in the negative direction, so it's minus Fg times the sine of theta. Now, let's consider the perpendicular direction. Okay, let's put these together. Now, the perpendicular direction, Fn it's only pointing in the perpendicular direction, so its component is just Fn, the magnitude of the force. Now, what about Fg? So we want the perpendicular component, that's this guy here, and it's going in the negative, so remember this is the positive perpendicular direction, and it's going into the plane, and so it will get negative, and because it's the adjacent side to theta, it's negative Fg times the cosine of theta. Okay, so let's put it together what we just said. We said that for the parallel direction, we have, it's right here, we have negative Fg sine of theta. So F net parallel is negative Fg sine of theta. Since parallel is kind of a long word to write, I'll just write it as two parallel lines. So I have now that the net force in the parallel direction is minus Fg sine theta, but we can now use Newton's second law, the second law. Okay, in the parallel direction, mass times acceleration in the parallel direction is equal to the force in the parallel direction. Okay, and we said that the force in the parallel direction, the net force in the parallel direction is minus Fg sine theta. So we can solve for the acceleration in the parallel direction. It's negative Fg sine of theta divided by m. Now let's plug in the fact that Fg is the force of gravity, that's m times g. Okay. And so I have minus mg sine of theta divided by m. And we get that A perpendicular is minus g sine of theta. Okay. Actually, we had already talked about this when we were talking about inclined planes on frictionless surfaces. If you tilt the plane by an amount sine of theta, then the acceleration down the plane is g sine theta. If I'm taking the parallel component where going up the plane is positive, then I would say it's minus g sine of theta. And so plug in g is 9.8 meters per second squared. The angle was 30 degrees, and so we get minus 4.9 meters per second squared. So the acceleration is 4.9 meters per second squared down the plane surface. Now, the other question was, what is the normal force? So for this, we're going to take a look at what's happening in the perpendicular direction. So in the perpendicular direction, remember we had in the perpendicular direction, we have that Fn has the component Fn, because it's going straight off the plane. Fg has a perpendicular component, this guy over here. It's minus, because it's going into the plane, minus Fg times the cosine of theta. Alright, let's use that here. The perpendicular, net force perpendicular is Fn, and then minus Fg cosine theta. Now, we'll use this shorthand for perpendicular. And so now we'll apply Newton's second law. We have the net force in the perpendicular direction is 0. And then, so we can just say Fn minus Fg cosine of theta is equal to 0. And therefore, Fn is equal to Fg cosine theta. Fg is m times g, that's the force of gravity. Plug in the values, m is 2.0 kilograms, g is 9.80 meters per second squared, and we have the angle of 30 degrees. So we have cosine of 30 degrees, and we get 17 meters. Okay? So that's everything I wanted to say about inclined planes. Now, we will say more about inclined planes in Tuesday's lecture when we talk about friction. The next thing I want to talk about is accelerating elevators. Okay, so let's consider a person that's standing on a scale in an elevator. Okay, so what is a scale? It's just something that somebody stands on. It reads a force. Okay, and so let's say the person has a mass m. Let's say positive y is playing up, and this is my accelerator with some cable that's holding it up. Okay, that's the elevator here. So this is the scale, and what the scale is doing is it pushes the person upwards with some normal force, Fn. Now, by Newton's third law, so I guess I was mistaken. We're actually going to talk about Newton's third law here. By Newton's third law, the person is pushing the scale downwards with force Fn. So the scale pushes up with Fn, the person pushes down on the scale with the force Fn. This is the force that will be displayed on the scale. So scale is just reading how much force the person is exerting on it. Okay? So now if the elevator is not accelerating, and then the net force is 0. Okay? So if we have if the elevator is not accelerating, then the net force on the elevator must be equal to 0, or the same thing, if the person is not accelerating, then the net force on the person is 0 by the second law. Okay, so what we're saying is that this is F net is equal to 0, MAY is equal to 0, so acceleration equal to 0. This is just actually, you could say, just Newton's first law. So now let's look at the forces acting on the person. Okay, in this very simple case where there's no acceleration. So we're not doing no acceleration. No acceleration in this case. Very simple. So we have y plus y pointing up. There's no acceleration, so this person, we have gravity pointing down, Fg. We have the normal force of the scale pushing the person upwards. Okay, so now let's get the net force in the y direction. It will be Fn with a positive sign from the normal force from the scale. There'll be Fg, it's pointing down, so that's why we have minus Fg. Okay, so we have Fn minus mg because Fg is m times g. Now we said that there's no acceleration, therefore from Newton's first law, or second law, either one gives it to you, the net force must be equal to 0, so therefore Fn minus Fg is equal to 0, and therefore the normal force is equal to the force of gravity with m times g. Alright, this is pretty boring. You knew this. If there's no acceleration, this scale is just is not accelerating, then as you expected, the scale reads the weight of the person. That's what a scale is kind of designed to do. However, let's make life a little bit more interesting, and let's consider an elevator accelerating upwards with the magnitude a. So the elevator is going up and getting faster going up. Okay, it's not constant speed, but it's getting faster, it's going up. and the magnitude of the acceleration is a. So in other words, ay is equal to a. Okay, so positive number a. So in this case, because we have an acceleration, the net force from Newton's second law is m time in the y direction is m times ay. But we said ay is just what we call a. Now we still have this picture that the forces acting on the person is the normal force of the scale pushing the person up, and the force of gravity pulling down. Now the net force will once again be Fn because it's positive direction, and this is in the negative direction. Okay, so sorry, let's draw it this way. So we have a positive for Fn, and we have a negative sign for the Fg. Okay, negative sign comes in because it's going in the negative direction. And so we have Fn minus mg. All right, now we said that the net force is Fn minus mg, but we also know from Newton's second law that it's equal to the mass times acceleration. So we can put this together. We have it's equal to the mass times acceleration, but here's a formula for the net force. So Fn minus mg must equal ma. All right, so remember, when we did the case with no acceleration, there was nothing on this side, and we just said Fn must be equal to mg. But now we have an acceleration on the right-hand side, and so when we solve for Fn, we will get mg plus ma, or if you want, m times g plus a. Okay? So the normal force will be bigger than the weight. It will be bigger because we're adding some additional thing here, the acceleration, to g. So the scale will read a force larger than the weight mg. That kind of hopefully makes some sense. If you are accelerating upwards very quickly, you'll feel it in your legs that you feel rather heavy. Your apparent weight, sometimes people use that term apparent weight, will be m times parentheses g plus a. So you add this acceleration of the elevator to g, and you multiply by m. That's just a shortcut of remembering what the result is. The derivation is exactly this. We have the net force, Fn minus mg, must equal to ma from Newton's second law. And then we solve for Fn, we get m times g plus a. Now, let's consider when the elevator is accelerating downwards with magnitude a. Okay? In other words, ay is negative a, where a is a positive number. In this case, F net y will be, again, may, or negative m times a, because ay is negative a. Now, we will still have that the net force will be, this guy is in the positive y direction, and this is in the negative y direction, so it's Fn minus Fg, or Fn minus mg. But, okay, so this is all the same. Fn minus mg is equal to the net force, but we said the net force by Newton's second law is minus ma, so we have minus ma over here. So when we go to solve for Fn, we have a minus ma sticking out here, and so Fn is equal to m times g minus a. So we're cutting into this value of g, so it will be g minus a times m. So the net force will be smaller than the weight m times g. Okay. Hopefully that makes some sense. If you're accelerating downwards, the elevator is accelerating, it's getting faster downwards, and then you'll feel lighter on the elevator. Now, if you have the very, very scary experience where the acceleration has a magnitude g downwards, okay, so a is g, remember we're saying ay is negative a, so it will be negative g for ay. So we're saying ay is minus a or minus g. Then the elevator is in free fall, so you really are falling. And in that case, if you were falling with the scale underneath your feet, it's probably not surprising that you won't actually register any weight, apparent weight at all, because then when you do Fn is equal to m times g minus a, you get g minus g, which is 0. So when the elevator is in free fall, the scale reads nothing. There's 0 force. Okay? Now let's just consider some examples where we have tensions and various forces, so you get a feeling for some of these applications. Let's consider a mass m that's being pulled by a string with tension T at some angle theta from horizontal, as shown here. What is the normal force exerted by the frictionless horizontal surface? Okay. All right, let's take inventory of what forces we have. We have tension T here going at this angle. We're going to resolve it in the x and y direction, the horizontal and vertical directions. And we have Fn going perpendicular, so that's vertical upwards. And then we have force of gravity going vertically downwards. Okay. Now, there is no acceleration in the y direction. Why? Because the block is just moving horizontally. Okay? And so if it was accelerating, well, first of all, it couldn't accelerate into the surface. That would make the mass somehow embedding into the surface, which doesn't make sense. And we're not told that the mass lifts off the surface. So there's no acceleration in the y direction. So that means Ay is equal to 0, and the net force in the y direction must be equal to 0. Now what we will do is calculate the net force in the y direction. So we have the normal force from the surface pushing up, that we have Fn, and then we have the force of gravity. It goes straight down, so that we have a minus mg. Then we have the component of the tension. That's this perpendicular component with a positive sign t sine of theta. Theta is here, so it's the opposite side, so plus t sine theta. Now we put these together. This is the net force, but the net force we said is 0. So therefore we have Fn plus t sine theta minus mg is equal to 0. Okay. So now we can solve for Fn. It's mg minus t sine of theta as a formula. So if you had numbers, you could put them together and get the normal force. Let's do one other problem. Suppose we had an example like this. By symmetry, so we have two strings attached to another string that's vertical. Okay, so we're going to take positive y direction like this. And we're going to make the strings have the same length. And by symmetry of the system, I mean I flip around this symmetry axis and it looks the same. These two angles will be the same, and let's say that the angles are 30 degrees for both of them. And let's say the tension in this string, which will be equal by symmetry to the tension in this string. These have both tensions T1, and this string here has tension T2. And the question is, if this is a 10 kilogram weight, a 10 kilogram mass, that's pulling on the string, then what are the tensions? Okay, so let's first get the easy one. So let's focus on the 10 kilogram mass and try to get T2. Okay, so we're just focusing on the 10 kilogram mass. These other tensions really don't touch the mass, so I've drawn them, but kind of I should just ignore all this. We have T2 pulling up. We take positive y direction being up. We have the weight of the mass being pulling it down. So we have 10 kilograms times g, 9.8 meters per second squared. Since it's not accelerating, it's just staying there, the acceleration is 0. This is equal to 0, so therefore F net in the y direction is m times ay, which is 0. So therefore, the net force in the y direction must be 0. Now let's just take inventory of what the net force is. We have T2 in the positive y direction, and then this weight is going in the negative direction, so we have minus 10 kilograms times 9.8. We said the net force must be 0, and so we can bring this thing to this side, and we get that the tension T2 is 98 newtons. Now that we know what T2 is, it's 98 newtons, we can take a look at what's going on here at this intersection, okay? The intersection of the strings. So we're going to consider the intersections between the strings. Alright, since nothing is accelerating, so if you want, you can think of there's like a very small mass here with 0 mass if you want. There's no acceleration. The point's not moving anywhere. Okay. So the net force must be equal to 0. Right? And so we have T1 going like this, T1 going like this, T2 going like this. So we need the net force to be equal to 0. We need both the x component to be 0 and the y component to be 0. All right. Now, if I solve for the x component to be 0, I don't really get anything that useful because I get this component, which is going to be T1 cosine theta, and this component, which is going to be negative T1 cosine theta because it goes in the negative x direction, that the sum of those must be equal to 0. But I kind of knew that already from the symmetry of the picture here that they would give me 0. I took advantage of that. So this is not helping me because I already did this. So we're going to look in the y direction because we already did the x direction. Okay? So we need the net force in the y direction to be 0. And so the acceleration in the y direction is equal to 0. Okay? I make this little comment. So actually this is also 0 because there's no mass here. So this is 0 for two different reasons. One is the fact that there's no mass here, so we get this equal to 0. The second reason is the acceleration is also equal to 0. Okay, now let's look at the net force in the y direction. We have this component here going up. It's T1 times the side, so it's the opposite side to 30 degrees, so it's sine of 30 degrees. We have another 30 degrees over here, so we have another T1 sine of 30 degrees. So we have T1 sine of 30 degrees from this, T1 sine of 30 degrees from this one here. And then we have minus T2 going down, so we have minus T2 here. And this is equal to 0 because there's no acceleration, or if you want, there's no mass either. Let's put these two together. We get 2T1 sine of theta. Let's bring T2 to the other side. Okay. It just so happens that 30 degrees, the sine of 30 degrees is 1/2. That's just a numerical accident. So we get this is equal to T1. It happens to be equal to T2. So for this particular problem, we get both tensions are actually the same. That's not the generic case. It's just special about this 30 degree angle. And so both are 98